Welcome to The Explainer. Today, we're taking a fascinating look into the world of predictive analytics. You know, we hear the buzzword big data literally all the time, right? But how exactly is all that data actually extracted from our everyday lives and used to change the real world? Well, in this explainer, we're going to dive into the math, the models, and the sheer computational power used to forecast outcomes, prevent disasters, and maybe even automate your job.
So let's jump right in. The big question we're tackling today is simple, but profoundly complex. Can an algorithm actually predict the future? And I don't just mean guessing tomorrow's weather. I mean forecasting incredibly complex events with dozens of moving parts. We're talking about everything from the outcome of a highly anticipated college football game all the way to life or death scenarios on our highways. The math says absolutely yes, and today we're going to see exactly how they do it.
Here's our roadmap for today's journey. First, the power of prediction. Second, forecasting NCAA bowl games. Third, predicting traffic injury severity. Fourth, we'll take a look inside the black box. And finally, number 5, the human impact.
All right, let's kick things off with Section 1, the power of prediction, looking at nowcasting and models.
Before we get into specific case studies, we kind of need to understand what it actually means to model and forecast the future using data. So the key thing to remember is that traditional modeling, like time series forecasting, basically takes historical patterns, random variations, time trends, seasonal cycles, and aggregates them to make a pretty educated guess about what happens next. But with the explosion of big data and machine learning, researchers are taking this to an entirely unprecedented level. They aren't just looking at past sales records anymore, they're analyzing real-time human behavior.
To see this in action, just look at how researchers are scaling these predictions to track diseases. In one really cool project aimed at early detection of the flu, data scientists essentially acted like digital detectives. They used the Twitter streaming API to crawl a massive volume of flu-related tweets. Then, they ingested all that unstructured text into a big data platform, using IBM Infosphere and Hadoop to run parallel computations. And the result? Absolutely wild. They mapped popular symptoms and locations, revealing a staggering 91% spatial temporal correlation between flu-related social media traffic and actual clinical flu outbreaks. They could literally nowcast the flu before the clinical records even had a chance to catch up.
But how do you actually go from a bunch of raw tweets to a highly accurate prediction? Well, data scientists rely on a very structured process, often following something called the CRISP-DM methodology. It flows step by step. First, you collect and clean the raw data. Next, you build your specific classification and regression models. Then, you test those models, tabulate the outcomes, and finally, compare the prediction results. It's a rigorous, incredibly scientific approach to peering into the future.
Moving right along to Section 2, forecasting NCAA bowl games. Let's predict some college football.
College bowl games are kind of the ultimate sports puzzle. They're incredibly high stakes, bringing in millions of dollars and massively boosting a school's athletic reputation. To predict these games, researchers gathered a truly massive data set. We're talking 8 complete years of data covering 244 bowl games. It's essentially a giant recipe mixing 36 different variables, things like offensive stats, defensive yards, home winning percentages, and conference strength, all to predict just a single game's outcome.
To figure this out, researchers broke their approach down into 2 completely distinct models. On one side, we have classification modeling, which is just a binary choice predicting a discrete win or loss, pretty straightforward. On the other side, though, we have regression modeling, and this one is much trickier, because it actually attempts to predict the exact integer point difference between the 2 teams.
So to find the best predictor, researchers used a stratified 10-fold cross-validation method to test out 3 popular data mining techniques. And the results? Totally decisive. Decision trees were the undisputed winner here. The classification and regression tree model predicted the correct football outcome over 86% of the time, totally outperforming support vector machines and artificial neural networks. And what's really great is that decision trees aren't just highly accurate. They're actually way easier for humans to understand and deploy in the real world.
Now let's raise the stakes for Section 3, predicting traffic injury severity, where we'll be analyzing crash factors.
So why does this matter? Well, beyond the deeply tragic human cost of over 30,000 lives lost every year to traffic accidents in the U.S. alone, these crashes cost taxpayers more than $230 billion annually. Let that sink in. Predictive analytics isn't just some fun academic exercise here. Identifying the root causes of crash-related injury severity is absolutely critical for saving lives and saving billions of dollars.
To figure out exactly what escalates a crash from a minor fender bender to a fatal accident, researchers pulled data from the National Automotive Sampling System General Estimate System. They merged accident, vehicle, and person files into one massive matrix containing almost 280,000 unique records. Acting like digital detectives, they used complex algorithms to sift through hundreds of thousands of rows of data, looking at environmental conditions, vehicle weights, behavioral factors, and ultimately managed to narrow it all down to 29 highly relevant variables.
Using this massive dataset, they built 4 different predictive models. Now, interestingly, the hierarchy of success changed completely from our college football example. In this highly complex nonlinear domain, the support vector machine took the lead. Because it's specifically designed to model highly nonlinear, complex problems, the SVM algorithm achieved an incredible overall accuracy of over 90%. In this case, it handily beat out decision trees, neural networks, and traditional logistic regression.
By running analytics across all these models, researchers pinpointed the most prevalent risk factors that dictate how severe an injury will be. The top 4 crash culprits identified mathematically were whether a seatbelt or restraint system was actually used, the exact manner of collision, like a front end versus an angled impact, whether the driver was ejected, and finally, the results of the driver's drug test.
Which brings us to Section 4, Inside the Black Box, focusing on sensitivity analysis.
Look, it's one thing for a machine to just spit out a prediction, but how do researchers actually figure out what these complex AI models are thinking? Well, they use a really vital technique called sensitivity analysis. You see, artificial neural networks are often called black boxes because they process highly complex, non-linear relationships that our human brains just can't easily track. Sensitivity analysis lets researchers basically peer inside by systematically perturbing or slightly tweaking the inputs in a trained network and then carefully observing how the outputs change. It's how they extract actionable, life-saving rules out of a giant web of complex math.
And this analysis uncovers some incredible nuance. When researchers broke the data down into a 5-class prediction problem, ranging from absolutely no injury all the way to fatal injury, they found that different variables matter depending on the exact severity of the crash. For fatalities, seatbelt use was by far the most critical determinant, but for lower-level minor injuries, seatbelts were actually far less significant, and strangely enough, the driver's gender became a key predictor.
The models also mathematically validated something that's highly intuitive but vitally important to prove. Age becomes an increasingly significant risk factor as the level of injury severity increases. The data unequivocally showed that older passengers face severely elevated risks in serious accidents compared to younger demographics. The math just completely backs up the intuition.
Finally, we arrive at Section 5, the human impact, looking at AI automating jobs.
We've seen just how powerful these predictive systems are, but what does all this actually mean for the future of our workforce? There's a pretty sobering reality unfolding right now. AI is no longer just a threat to manual labor. It is rapidly automating cognitive, white-collar jobs too. Equipped with natural language processing and real-time big data, intelligent systems are already acting as robo-marketers, writing highly targeted ads. Robo-financial advisors are predicting markets for just a fraction of what a human charges. IBM's Watson has demonstrated an astonishing 90% accuracy in diagnosing lung diseases compared to just 50% for humans. And the Associated Press, they are already using AI to write completely error-free financial and sports reports. No way, right? But it's true.
Now you're probably wondering where your own career falls on this spectrum. Studies highlight a really stark contrast. The highest risk jobs, the ones facing near-term automation, are cashiers, toll booth operators, fast food employees, and drivers. Basically roles where tasks are highly repetitive and predictable. On the flip side, the lowest risk jobs include nurses, doctors, youth sport coaches, and social workers. These are the safe, highly social professions that require deep human empathy and complex physical intervention.
To really summarize this paradigm shift, consider this observation from McKinsey & Company. They noted robots are also increasingly capable of accomplishing activities that include cognitive capabilities once considered too difficult to automate successfully, such as making tacit judgments, sensing emotion, or even driving. The boundary of what a machine can actually do is moving remarkably fast.
So I want to leave you with this final thought to ponder. We've seen today how data scientists use machine learning to track flu outbreaks, perfectly call the outcome of college bowl games, and unravel the incredibly complex web of traffic fatalities.
As these models become faster, cheaper, and profoundly more accurate, the real-world implications are only going to grow. Think about it. If an algorithm can predict a devastating crash and then seamlessly turn around and write the news report about it, is your job next? Thanks so much for joining me for this explainer, and we'll see you next time as we continue to break down the complex forces shaping our world.